Now that we have an understanding of how 2D particle equilibrium works, we can extend it out to objects that are in 3 dimensions, so 3D particle equilibrium. So not too much has changed, we just have to generalize it a little bit. So it's still going to be true that if we're in static equilibrium, the sum of our forces still has to be 0, or in this case, the 0 vector. But now we could have forces acting not only in what we generally call the x and the y direction, but the z direction as well. So what does that mean? It means the right-hand side is now equal to 0i plus 0j plus 0k, if we're from the Cartesian component perspective. So what do we want to do? We're going to have now 3 independent scalar equations that we can break this one vector equation into. Now in 2D, this third equation was always there. The sum of forces in the z was 0. But in 2 dimensions, we never have forces acting in the z, so it's always just 0 equals 0, which we don't need to include. But now in the 3D case, with potentially x, y, and z components of forces, we do need to explicitly write that third equation as well. So every free body diagram in 3D gives us these 3 linearly independent scalar equations. All right, so where are we going to get them? Well, still, that's going to come from a free body diagram. But now the free body diagram does get a little bit trickier to draw when we're in 3D, just the mechanics of it, of representing 3 dimensions on paper rather than 2. That gets a little bit harder. And in the dimensioning step, all those same rules from before are still going to apply of what needs to be in the free body diagram. But when we look at the dimensions, that 4th step, I really recommend when we're in 3D, you don't try to include angle measures in your diagram. Just putting coordinates of important points is typically going to be a much easier way to go, because we're going to use those coordinates to find position vectors or displacement vectors that we're then going to normalize to find unit vectors. So working from the coordinates is really going to accelerate that process. And again, we still need to have a coordinate system labeled and explicitly put into our diagram, and then the coordinates we use are based on the coordinate system that we were either given and just copying down, or that we establish ourselves. So this 3-dimensional free body diagram is used to write equations 1, 2, and 3, those equilibrium equations now. But what we can do is we can break down, before we get to writing these 3 equations for each free body diagram, representing all of the forces in their Cartesian component form first is really going to make the process of writing the equilibrium equations much easier and much faster. So getting up front all of the unit vectors we're going to need together, breaking all of our forces into their Cartesian component form. Then when we write the equilibrium equations, just picking out the I, the j, the k components of all those forces is going to make this a lot quicker to get our equations. And then we're going to solve our simultaneous equations for our unknowns. So here, we're typically going to have more equations than we had for 2D particles, but as long as we go through those same procedure steps of how do we solve the problem, well, do we have enough equations for how many unknowns we have? If we can establish that it is a solvable system, then the solve step, whether it's by hand or using some sort of tool, we can go through and be assured that we are going to get a unique answer for our problem. So what are some things that arise in 3D that we need to be a little bit cautious about? So like I said, I really want to emphasize this, starting by writing down all the coordinates of important points, like 2 ends where a rope is attached, for example, is really going to aid us in then drawing the position vector or writing the position vector, and then using that to find the unit vector. So if we do all that work up front, worry about that first, and then we can go into our equilibrium equations. So a lot of times we're going to have some forces we're asked to find the magnitude of. So this happens a lot when we have a cable or a rope that we want to know what is the force in that rope to maintain equilibrium. Well, recall from the previous section when we were first talking about vectors and vector representation, a vector f can be represented by its magnitude times its direction, which generally we just generically wrote as like f times u hat. So what we don't know usually in these problems is the magnitude of force in things like cables and ropes, but we will have the ability to calculate their direction by establishing the unit vector that points in their direction. So if we look here, here's how we can write, even if we don't know the magnitude, we can still write out the components of vectors with unknown magnitudes. So some vector f we can represent as, for example here, if we knew that it would lay along the unit vector 2/3 I minus 1/3 j plus 2/3 k, well, that unknown magnitude f we can simply distribute into the I, the j, the k components of that force. And then what do we have here? Well, when we go to the step of writing down our equilibrium equations, let's say we want some forces in the x direction, well, we've already written this out in component form. The x component of force F, vector force F, is going to be 2/3 F, magnitude scalar F. So that 2/3 F is going to go into the x equation, along with other x components of forces. When we get to the y equation, well, again, we just want to pick out the coefficient in front of j. In this example, negative 1/3 F. And then in the z equation, the k component is positive 2/3 F. So that unknown magnitude F will appear in all three equilibrium equations. But when we go through the equation writing step and we count up our unknowns and we count up our total equations, it's that same unknown magnitude, that same variable that's appearing in all three equations. So it's only one variable. It is in three different equations, but it would only count as one unknown as we go through.